All right, let's get started for this week. Hopefully you guys had a good weekend this time and fun with our tool Mars. And tonight we're supposed to coming to the class with review of the register, usage of the register, and how to store values in the registers and those things. Mainly the register manipulation. This is very easier side of the assembly programming. If you have any question or any issues or anything like that you want to bring up, please let me know right now while I'm going
Yeah,
into.
I do have a question, Professor.
Yes, Christopher.
I think I emailed you earlier about trying to get the Mars simulator installed on my laptop, and it's still not working.
So did you try to run it directly with the Java command line?
Yeah, so it gave me, I'm on Mac, and it gave me a security error, and then I went into my system preferences and allowed it to install, but then it keeps giving me another error to check my console for errors, and it won't let me install the program.
So it's a jar file. It's a Java archive file.
Yeah, it's a Mars 4 underscore 5 jar file.
Right. And I usually have in my Windows system, I have a batch file, batch run file, which calls simply the Java with that argument. I see. So anyone with using the Mac system has successfully run Mars. Want to bring in that experience?
Yeah, I had the same problem, but when I went to go open the file, I instead did control click on the file and then opened it. And I think that what that does is it does like a force open regardless of the security.
So I tried that right now, and it says Java application launch failed. Check console for possible errors. Message related to user downloads Mars 4 jar.
Maybe try copy pasting that error message into Google.
Okay.
Yeah. Anyone else had similar problem running Mars?
Professor?
Yeah.
What kind of problem are you talking about?
Sorry, I couldn't hear your voice clearly.
What kind of problem are we talking about with Mars?
So Jacob is trying to run the that Mars tool on the Mac system, and it is giving us some security error, even with the command line running of the Java and that jar file.
I see. Okay.
Yeah, at first it was giving me like a security error. It wouldn't let me install the program because it said it didn't know if it was malware or not. But I went into system preferences and security and allowed it. But now it's giving me a different error.
Hey, Christopher, do you want to share the screen with you rest of the class so that someone?
Yeah, I can share the screen.
Let's do that. I don't use Mac system myself, so I won't be very much useful in that area. So
can you guys see the screen?
Yeah.
This is the error it gives me when I try to launch it.
This is just like a weird idea, but what if you moved it out of the downloads file?
If I moved it out,
sometimes like Mac isolates that. I don't know for sure though.
Okay, I think that might have got it working. I think so. Yeah. Now it's installing.
All right, there you go.
No, it's on. Just the tool itself with nothing to install there.
All right, thank you guys. I appreciate it.
Oh, this is very good. This is very good. Thank you very much. Appreciate to all.
I'll stop sharing now.
Okay.
Professor,
Yes.
I had a problem opening the ASM files for the assignment.
Okay. Do you want to share your screen?
Yeah. Okay, so if I go to, I have it in my, can you see my screen?
Yes, I see your desktop.
Okay, so I have it in this folder under assignment 1. And then if I go to my Mars, file open, then I'm gonna go to my desktop right here, and it's just empty.
Oh. Okay. Which one you are trying to open? That main program, right?
I'm trying to open this folder in desktop.
What is that path for that folder?
It should be in under my user, under my user right here, and then these are my folders. It should be under desktop.
Okay.
But like even my documents or like my downloads, none of them have any.
Yeah, can you try to make another folder and see if that like desktop may not be, I don't know.
Like in the desktop.
Again, I don't use I don't use Mac, so I don't know what that system is doing. It should pick up things.
I've also seen this problem before when I was using my Mac for the Eclipse IDE, and I think it was some weird thing where it just couldn't access files on like your user level, and I had to put all of them up on like a higher level folder. It was really weird.
Okay.
Yeah, put things in the downloads and let's see if we can pick up from the downloads.
Not, I don't know.
No?
Well, even the download is empty here. I guess I could.
But you could see stuff in your like your user folder or something, right?
Oh, let's see.
Yeah. See, I don't know. That happened to me once too, and in the end, I just moved everything into the user folder, and I just left it there instead.
Okay, I guess I'll try that and see what happens. Thank you.
Okay, all right. So any other challenges? These are all interesting practical challenges. And nothing, by the way, nothing to do with the assembly programming. Okay. Let's see. I have some question. I saw some question on the discussion. Okay, Ricky asked about the zero register. Yeah, you are right, Ricky. Like zero register is a constant zero, and many pseudo instructions and other type of instruction need to use zero more frequently than you can imagine. In the higher level program, you don't imagine that like you need to use zero frequently, but in low level program, you'll see for the pseudocodes and for other type of instruction, frequently you need to use the value zero. So that's why there is a dedicated register which always stores a zero. So that's the purpose of the zero register. Makes sense, Ricky?
Yeah, that makes sense. Thank you.
Okay, Tori says, how does the ORI operator work and how does it help to storing the large numbers? Okay, so yeah, let me explain that. That's a good question. Let me share my whiteboard, Jamboard, and let's do this. So let's say, let's take an example of 8-bit registers. Okay, 8-bit registers. So let's draw a box for each bit. Okay, and let's do 8 of them. So that would make us 8-bit. Three, the 6, 2 more. Okay. Now, if it is an 8-bit computer, then my immediate instruction, it can have a value represented by 4-bit of 4-bit of float. Why? Remember, like in our MIPS instruction format, what we have seen that like if it is a 32-bit, let's say if it is a 32-bit, 32-bit, our immediate field is half of that immediate value field. Okay. So that means any instruction that you can think of to manipulate a register with an immediate value, something to store a value or things like that, it will operate on this part because that's the range of the value you are able to specify within those instructions. For example, instruction like add I, right? Instruction like even load immediate. Load immediate is a pseudo instruction which I believe is add IU or something like that. These things are what you are trying to do. Let's say we are trying to load in register 2. So register number 2, add I. Now you need to specify some value, right? So 30, 40, 50, etc. So this essentially means the $2 will be loaded. Actually, okay. Let me revise something. This is not $2. This is the instruction. Let me draw the register itself. So this is a 32-bit register, $2. And this value, which is should be stored as a part of the instruction, it will be stored down here. So this part only, like the part of the immediate values. So that means my register, target register, can be half filled. The upper part cannot be filled up because immediate instruction doesn't have that many value range. You cannot just have an instruction add I with immediate value more than 16-bit, right? So that's why one single instruction like add I, li, which is single instruction, other instruction, there are other mathematical instruction you can think of, whatever you can come up with, you are bound with 16-bit value. Then the question becomes how we can load more than 16-bit value, because my $2 is a 32-bit value. I could load a larger value there, and I may need to load larger value there in my program. So what is the solution for that? So let's do that discussion in terms of our 8-bit registers. Okay, let's say it's a 8-bit computer, means my this value is 8-bit total instruction. So this becomes like 4-bit. So instruction can embed 4-bit worth of value inside that. So let's say I have come up with something like add I. Let's say this is $2, add I $2 $0 with, let's say, 10, or okay, let's use hexadecimal form. And also let's try to make our target. Our target is to load the larger value, which belongs to a bit pattern of 1, 1, 0, 1, 0, 1, 1, 1. Let's say this is my target value, whatever that binary 8 bits represent, that value. So with the add I, what can we do? We can maximum do like, what is the hex representation of this? This is 1, 2, 4. This is hex 7. And this is hex 8, 4, 12, 13, D. Okay, so we can do like 7, add I 207, which will load here 0, 1, 1, 1. Now, how can I load the other part, this upper part? How can I load it? So here, the solution. Instead of doing this, let's do this way. Load upper immediate. Let me also delete. Okay. Load upper immediate $2 with D. So this instruction will do what? It will load 1101, which is D, and 0000 on the rest of the bits of this 8-bit register. Now we do OR I $2, $2, $7, which essentially means, this really means you are taking the bit pattern of the register 2 and logically OR it, bitwise OR. So this is like bitwise OR, logical OR with this, right? So essentially what it will do, like my $2 value, previous value was 1101, 0000, and I am trying to OR it with 7, which is like 0000, 1, 0, 1, 1, 1. Logical OR, you do, it basically become 1, 1, 1, 0, 1, 0, 1, 1. Right? So at the end of this instruction, my value would become, value stored in the register would become 1001, 0, 1, 1, 1. So that's how it helps us to load a big value, larger value, which need to be represented with more than 16 number of bits in case of MIPS programming. That's what we do. Louis and ORI, that's how the ORI helps. Try this is okay? This one, are you okay?
Yeah, that makes more sense.
All right.
Professor,
Yes.
I'd like to add on a question onto this explanation. So after load upper immediate, you use the ORI.
Mm-hmm.
Can we use ADA instead of ORI over there? Because the ADA anyway only affects the last, the second half, right? Second half of the memory space.
Okay. Apparently you can, but let's try to see an example, right? So ADI, first of all, it's not an bitwise OR operation. It has a more significance to it. What is that significance? Let's say you want to do add here, right, instead of OR. So what the result would be. Here, the result would be same. Like if you add this one, result would be same. However, let's pick up another example and let's see if we can apply that apply that thought. So let's say
Professor?
yes.
Yeah, I didn't say to add. I didn't say to add I didn't say to add hex 7 to the value at $2. Like the first ADA instruction that you wrote, ADA at $2, $0 and 0x7. So over there, what I'm assuming is happening is 0x7 is added with $0, and that result is being stored in $2.
Right.
So can't that instruction be used after load upper immediate?
Yeah, that's what I'm coming. That's
I
what I'm
see.
coming. So what I'm trying to, so what you are trying to propose here is this. Instead of this, you want to propose add I instead of this one, right? Instead of this one, alternate add I $2.07, right? Raul?
No, $2, $0.07.
$0.07. That would be completely wrong, right? Because these results, right? These results is completely uh, 0, 0, 0, 0, 0, 1, 1, 1. So this result, addition of this result is still 8-bit. So your things will become 0, 0, 0, 0, 0, 1, 1, 1. So
So it
your
overwrites the first half.
what's
So it will overwrite the first half.
yeah, yeah. So add I is always like full bit instruction, like whatever number of bits. Like if it is a 8-bit computing system, result will be 8-bit. If it is a 32-bit computing system, result will be 32-bit. So that way, in a sense, it will override your upper half, basically.
So the result will be 32-bit, even though it can only produce a maximum number of 16 bits.
No. Okay, add I or add or anything, any arithmetic function produces a full 32-bit in a 32-bit MIPS.
I see. Okay.
It's the only that how much from the typing the assembly program on the add I statement, how much you can add as a second operand. And that value is limited to 16-bit value.
I
So
see.
this 16-bit value first transformed internally into a 32-bit, it extended, it bitwise extension happens, and then added on top of the value of this register, which is already 32-bit.
I see. Okay. So if that register already happens to be some number which is larger than 16 bits, then the result of ADI will also be something that's larger than 16 bits with significant numbers.
Right. It doesn't matter whether this register is holding a value of more than 16-bit or not. It is a 32-bit value always.
I see.
Right?
So it's not guaranteed that an ADI, sorry.
So you may not be using the upper half of the bits. So they can be all zeros, but they're still 32-bit value.
But they don't need to be zero. They can be non-zero. The upper values can be non-zero.
Yeah, exactly. For larger value representation, they will be non-zero.
I see. Okay, and that's where my confusion lied, false assumption lied. All right, thank you.
Now, are you clear now?
Yeah, that clears my assumptions.
Okay, all right.
Can I add a question too?
Yes.
It was just some things I needed to clarify about ORI. So the first one would be what's the second $2 supposed to do there?
What's the second dollar?
The second $2 sign after ORI. Yeah. What is that one for?
That one is also $2. It is almost like writing A equal to A.
I know, but what is the purpose of it?
So basically the purpose is, let me just reverse our discussion. Yeah. So purpose is this. You have a pattern of 11010000 at this point in the $2.
Yes.
So it is telling that grab that bit pattern, like this bit pattern, and OR it with this bit pattern. and store it back into the same register.
Okay, and so that leads into my second question actually. What exactly is OR supposed to mean? Like, is there like
Is
a meaning behind
the
this?
logical OR
Yeah.
or math 32?
Uh-huh.
Sorry, math 42.
Yeah, I know what a logical OR is. Is this like, I mean, how does it like apply in this situation?
So this is like, okay, remember like this, these are the logical OR table.
Yeah.
Like if it is bitwise, let's say 2 bits A, B, and the outcome is Y. So false
Yeah.
and false is false, false and true is
Yeah, I know that. Uh-huh.
right. So it is applying just like that, like false and true is true, false and true is true, so on and so forth. False and false is false. So that's the bitwise.
Oh, okay. Yeah. See, all I was confused about was like what it was doing to the table at that moment. Okay, that makes sense though.
Yeah. So it's not a programming or logical or like you used to do in the high level program that
Yeah.
that
So
and
it's just using it like
operator
a
and
math operation. Then.
pipe operator. It's not that.
Okay.
By the
Okay.
high level programming also has bitwise operator as well. You can
Right.
use it in your program. Okay. So Fong, that clears up your
Yeah, that's good for me. Thank you.
okay. All right. That's great. Great. So now what else? Anything else? Any other things you guys want to bring up?
I have a question about the submission of our ASM files. I already submitted mine, but I just realized that I didn't comment my name somewhere in the code. What is commenting our name in the code necessary or no?
Yeah, when you upload and yeah, that becomes tagged with your name.
Okay, so it's okay if I just resubmit my assignment, right?
Yeah, sure. Yeah, it's fine. And resubmission, since you brought up that, like when you resubmit or even for the next assignment where you are be uploading the same file name, you will see that Canvas will add one extension to it, -1, -2, -3. Don't worry about that. When evaluating, we'll change the file name. So don't worry about the automatic extension that that Canvas put on the submission, on the resubmissions, or if you upload the same file.
Yeah, that's what I was a little bit worried about. So I was just making sure.
No, that's fine. That's fine. It's we know that the extension will be ignored there.
Is there a certain format you want us to write our name on the assignment?
Not really, but inside the first comment line, maybe if you can just put your names there. That is a good practice, by the way.
Sounds good.
Okay. All right. Now, let's do one thing. How about a pop quiz? Let me see if we have it. Maybe I can give this quiz to you. Just give me 2 minutes. Let me set this up. Okay, all right. Now let me open up that poll. If you are ready for the pop quiz password. Okay, go to your Canvas and see if you can find out this pop quiz number 2.
Professor?
Yes.
Did you say we need to have our names in the comment section of our assignments? All of them?
It's not a must, but it's a good practice.
I see. Okay. It's just good practice.
Yeah.
Thank you.
Hey, someone said no on that pop quiz. Are you ready to enter the quiz password? Someone said no. Are you not able to access that quiz, or what is happening? Okay, 22 of 20 is done. Okay, and polling. Let me get the passcode to you. Hey, what is this passcode?
Professor,
Yes.
so what is the access code?
Yeah, just hold on. Let me. I need to change it. Just hold on. Just wait a minute. Let's see. Oh. Why it is not updating? Okay. Let me do one thing. Let me open up the chat and give this passcode over the chat. How about that? Let's see. Okay, here it go. Look at your chat. Okay, I think times are up for everyone. Let me see. How is the quiz? Start. Why don't I share it? Share the screen. Okay, this is your pop quiz summary. Average score 68%. Need to be proved. 100% is high score. Standard deviation 1.06. Okay, but yeah, let's make sure everyone is up to the pace, up to the and keeping up with the class. While I'm sharing this one, why don't I share your quiz one stat for the class? Where is that? Okay, share screen. So this is as a whole class, this is what your standing is. On the quiz one, passing rate is 88.9%, where B minus or better is 81.5%. You can see that like 16 of you students, more than 50% actually got 45 or more, 10 of them got 50. This is okay in the sense like since uh, I see this repeating pattern in every semester that first quiz goes a little bit lower because of the fact that this is a very new subject. All the concepts are new. You are new to my style of teaching, my style of questioning. So probably now, by now you are tuned up after this quiz one that what type of question I usually give in the quizzes and similar things will be coming in the exams. So now that you are tuned up, then I expect on the quiz two, we'll see better statistics or as a class performance. To start with, this is not bad. I can say this is, I don't say this is good. If it touched 90% or above on the passing rate, at least I can say it's a good stat. But it's okay. It is not bad either for the first time. All right, let's take 5-minute break at this point, and we'll be back with some interesting discussion after this. 6:50 is 51. We'll be back. Okay, now let's come back from our break and let's discuss some interesting topics of bit extension in light of what Rahul asked, and which is an interesting question, that for an immediate operation like add I or I, that kind of things, we are supplying an immediate value, which is of like 16-bit, half the bit value of a 32-bit system. So how that operation is done internally and how that result is manipulated, let's try to understand that part in a little bit detail. I'm going back to my Jamboard, sharing, and okay. Now see, we are interested in these two instructions. Add I, some target register $3. I'm adding the bit pattern value of $2 with an immediate value of hex 9. Okay, hex 9. And another operation, let's say OR I. Similarly, we are taking the bit pattern stored in the $2 register and doing an OR immediate operation or logical OR operation with a bit pattern of a hex 9. That's a bit pattern. Like how system manipulates these values internally. That's a question. And let's also assume this is an 8-bit computer. Right? So we can extend a similar concept in a 16-bit, 32-bit as well. But this is let's assume this is an 8-bit computing system. Now ask yourself, like this add I, this operation. What is, first of all, what is this type of this operation? This is an arithmetic operation. And also add I actually involves with signed value, means result can be either positive or negative, and you can supply both negative and positive values through these operands. Now what is that? That brings us the next question: what this value is in the decimal, like in a decimal value system, what that value is. Remember, like in our number system discussion, we did discuss about the 2's complement. 2's complement system. So there, a bit pattern of 09, which is something like this, 1001. In 2's complement form, this is really equal to -7, right? This is -7. And let's say I have the $2, I have the operand bit pattern as this. Okay, now what is that value is? That value would be, let's calculate, this is 1, 2, 4, 8, 16, 32, 64, 128, which is like 64 plus 8, which is 72 plus 4, 76. This is 77. This is 77, operand 1. So my expectation of this result, right, this implication would be $3 will be 17 plus of -7, which is, sorry, 77 addition of -7, which result into 70, right? And now how it is being operated. My operand 1 is $2, which is okay, 8-bit complete. Now operand 2 is 4-bit. So we can definitely like, let's say, bring this down into the operand section. 1, duplicate 0, duplicate 0, okay, bracket 1. That is the 4-bit, right? Half the bit length. So what will happen to this one? Okay. Someone can say, hey, why don't we just put zeros? Because, well, that's the natural electronic value in all these systems, right? So if we put it 0, now what this value represents in a 2's complement form?
9.
Yeah, this exactly. This is 9. This is representing. So instead of doing this guy, what we are doing really in this form, it is 77 plus 9, which is like 87. My result is wrong. I was expecting 70. So what we need to do, instead of putting zeros, we need to put 1 here, right? So if we make 1, everything here, then this guy is actually represents -7. Okay, you can calculate your own, like this bit pattern, what this 2's complement represents, but it represents -7. So essentially what we are doing, we are as if, let me delete it, as if we are picking up the MSB of this bit pattern, this immediate bit pattern, MSB, and duplicating it. Okay, so that is called sign extension. So it's a sign extension of value. So for this add I operation, sign extension of value happens, and then result is computed. So this is sign extension. So we pick up the MSB of this bit pattern and replicate it throughout the rest of the bits of this system, and then the operation happens, and then we get into this good value, like the 70, our target value, our expected value is 70. That's what happens here. Now with respect to that, let's try to do it. The OR I operation here is the same thing. So what we are trying to do here, instead of doing an addition, we are trying to do OR logical, not logical, bitwise OR between these two, like whatever that bit pattern is, right? So our expectation would be something like this: 0, 1, 0, 0, 1, 1, 0, 1. That is my operand 1, and operand 2 was given 1, 0, 0, 1, and we OR it. Okay, logical OR operation actually assumes zeros here. So 0, 1, 0, 0, 1, 1, 0, 1. So that would be our result, expected result. Now we see in this scenario, we really cannot do sign extension, right? Sign extension, if we do sign extension of this, will end up in this bit pattern, which will end up in a result of 1, 1, 1, 1, 1, 1, 0, 1, which is completely wrong result. We wanted to have this one. So in this case, we actually need to put zeros in these forms, right? So let me just delete, and we need to do, okay, we need to just replicate some zeros over here. So we need to put the zeros over here, zeros over here. And this is what we called zero extension. So there are two types of extension. One is called sign extension, sign extension, which is applied to arithmetic operations, and 0 extension, which is applied to the logical, bitwise logical operation. However, I said sign extension to be applied on the arithmetic operation, not entirely true. If we have something like this unsigned operation, add IU, this is mean add immediate unsigned. In this case, we will still have the 0 extension. So 0 extension is applied on the bitwise logical operation and unsigned arithmetic operation. Any signed arithmetic immediate operation goes with the sign bit extension. Question? Okay. All right. Now let's see what is coming up in the next day's lecture is very important. Next 2 lectures, actually all the lectures are important. However, these 2 lectures will be introducing you to the usage of the memory, like the memory system. So far we have reviewed how we can store, retrieve values from the register. Now we learn how do we store and retrieve values from the memory, and what are the data layout convention there. That's what the next lecture topic is, memory usage 2, and it has 6 parts of different explanations. Very important. We start with we have the memory model there. We start with the discussion, what is the different assumption a software program assumes about different section of the memory. As a device, the memory doesn't distinguish that, okay, this is my dynamic data section, this is my stack section, this is my text, this is reserved. It doesn't matter. At the very low level hardware electronics level, one can write anywhere in the memory. This sectional assumption comes from the software world, that they have an agreement. Software programmer, operating systems, all of them has an agreement that, hey, we will use this part of the memory for this specific purpose, or that part of the memory for that specific purpose. That is completely a software convention. So we need to learn what are those conventions. That is very important. And then we discuss about, like, this is the real life convention on the MIPS processor memory usage areas. And there are some little difference with when you go into the simulation environment of Mars. We discussed that difference here in this page. Then we move on to the different types of memory read and write instruction. In fact, there is only one type, like store word, load word, 2 types, 2 instruction, and variation of that. So load word, there are load half word unsigned, load byte unsigned, and it explains what it does really, like how the memory address is computed, etc., etc. And then we will talk about the load half word signed, and then move on to the store word, and then store half word and store byte, that kind of instructions and usage of them. Then we will do some experiment like pseudo load, pseudo store. So these 2 pages, previous pages, are describing the raw, the processor supported instruction. So this is the only format, for example, this is the only format that processor supports. Load word, and then some register followed by the some immediate value. Within open and close braces, there is some register, like, and that is the only form. But in the MIPS, provide through some pseudo coding, pseudo instruction, some other form of load word, store word as well. So that's what we'll be actually looking here. Like for example, this one is very much look like the primitive load word, but they are not. No, this one, these two looks like very primitive one. This one is primitive, but this one is not primitive. This is a pseudo. So you need to understand that subtle difference, though it looks like very similar in the formatting of that instruction. But if you assemble that code, you will see it is spitting out different machine code for these two instructions versus these two instructions. And we try to explain what is going on there. So from there, we talk about something called endianness, which is very important concept, big endian, little endian. Probably you have heard of this term. I'm not sure, may not, but it doesn't matter. We'll discuss that, what is that endianness of these, and then, yeah, so these are the all important concept. And then after that, we'll move into the lecture 9, which is possibly 2x harder concept than this one. So make sure you are on track. Like this is already, lecture 8 is already almost like 2x harder than your lecture 7 concept wise. Now lecture 9 would be concept wise 2x harder than lecture 8. So please make sure you understand the concept, each of the points, and I hope to get more and more questions from you on the conception side. Question? All right then, so tonight I believe your programming assignment 1 is due. Make sure you are on time on that, and next day also we have programming assignment 2 due, I believe. Please make sure you complete that within time. All right, good night and see you all on Thursday.